Okay, last video cut off without me knowing, so I finished everything. So I'm going to come back and complete this. Okay, so what we're doing, we're taking the total derivative, and right now I'm doing a kind of an illustration of why we typically, basically an illustration to give us an idea of when we use total derivatives and when we don't. Okay, so I had just shown you that here I have a function. It's a function of x and of alpha, but a function of a function of x and of alpha, but x is itself a function of alpha. So I've written that out here, and I've taken the total derivative of it here, where I have used the chain rule, and then I use the direct derivative. And I was saying, well, the reason why I have this term here is because I haven't specified the function. I haven't specified the x of alpha function. Okay, well then I went ahead and did that. So x of alpha equals alpha over 2. So then let's rewrite this. The derivative of f with respect to alpha is 4 times the derivative of x with respect to alpha plus 2 alpha. Well, the derivative of x of alpha, we can see here, is just 1/2, so we can plug that in. That equals 4 times 1/2 plus 2 alpha equals 2 plus 2 alpha, which equals 2 times 1 plus alpha. Okay. Now, if we know in advance what the function of x is, if we know what x is in advance, we can plug x of alpha into the function, and we'll get a function that is just of alpha. There's no x's in it, it's just of alpha. And then we don't need the total derivative anymore, because the total derivative is the same thing as the direct derivative. So let me just illustrate what I mean by that. So let's say I have f of x of alpha, but I'm just going to plug in what x of alpha is. So I'm just going to plug that in. And so what does that mean? It's going to be 4 times alpha over 2 plus alpha squared. Simplified, it's going to be 2 alpha plus alpha squared. Now when I take the derivative of f with respect to alpha, there's no x anymore. I don't have to use the chain rule because I've plugged it in and simplified. So now I just take the direct derivative. I get to this, which is 2 times 1 plus alpha. Okay, so then these are the same thing. So basically what I want to show by this is that we typically use the total derivative in a context when we don't necessarily have the whole function, or for some reason we don't want to write out or express the whole function in terms of all of the sub-functions, you could say. Let me give you an example of where we use this in class to try to make this a little bit more concrete, and I hope it becomes clear. So we know in class when we're doing an optimization problem that we create the Lagrangian function. So let me just create the Lagrangian function, and let's say the function is, we're doing a maximization over the variable x, y, and lambda. So here's my function. And if I take the first order conditions, I'm going to get the derivative of L with respect to x equals 0. The derivative of L with respect to y, set it equal to 0. And the derivative of L with respect to lambda, set it equal to 0. If we manipulate these functions, we'll eventually be able to calculate the optimal x, where x is a function of the parameters. Let's say there's just one parameter alpha. Y, optimal y, which is a function of the parameter alpha. And lambda, which is a function of the parameter alpha. If we take x star, y star, and lambda star, the optimals, and we plug them back in, we're going to get our indirect objective function, or our indirect utility function, we could say. All right, L, we plug that in, we get x star, which is a function of lambda, y star, which is a function of, a function of alpha, y star is a function of alpha, and lambda star as a function of alpha. Okay. Now if I asked, okay, what is the derivative of L star with respect to alpha? This is a case in which we'd use a total derivative. I don't necessarily have to specify what x of alpha is. I just know that x is a function of alpha. So let me take the total derivative. The total derivative of L with respect to alpha is equal to the derivative of L with respect to the optimal x times the derivative of x star alpha. So this is just the chain rule. We have to do the chain rule for x because x is a function of alpha. We also need to do the chain rule for y because y is a function of alpha. So we'll do derivative of L with respect to y times the derivative of y star with respect to alpha. We do the same thing for lambda because lambda is a function of alpha. So let's do that. With respect to lambda star times the derivative of lambda star with respect to alpha. And then we need to do the direct derivative of L with respect to alpha. So this is my total derivative. Now, just for completeness sake, I'm going to take this opportunity. I know this is a derivative review, but let me just reiterate the envelope theorem. When my function's maximized and I take a total derivative with respect to a parameter, I'll recognize in this total derivative that this term, L, the derivative of L with respect to x, at the optimal point is equal to 0. That's my first order condition. All right. The derivative of y with respect, derivative of L with respect to y is also equal to 0. That's my second first order condition. The derivative of L with respect to lambda is equal to 0 also because it's my third first order condition, which means all of these terms are 0, which means the total derivative of L star with respect to alpha is equal to just the direct derivative, which makes the calculation much easier. The fact that this is true is called the envelope theorem. Okay, thank you very much and have a wonderful day.